In the previous class, we discussed about various ground conditions, the suitable method of excavation in those ground conditions as far as tunneling is concerned, appropriate support system, and what are the precautions that one needs to keep in mind while going for the excavation in such ground conditions. Then we also discussed about the difference between swelling and squeezing phenomena. So, that was all about the ground conditions and related issues. Today, we will start a new topic, that is elastic stress distribution around circular tunnels. Since we will be having the derivation for the elastic analysis for the circular tunnels, so this may stretch over two lectures. So, to start with, let us first try to understand the geometry of the problem. So, to start with, look at this figure, and here you have this excavation in the form of circular tunnel which has the radius equal to A. That has been shown here. This tunnel has been excavated in an semi-infinite rock medium at a depth h, which is this. This is the depth between this point and this point, that is on the ground surface. You need to take a look here that this overburden depth is much larger than the radius of this circular tunnel. One more thing which we will be using quite often, tunnel and the topmost point is called as the crown and the bottommost point is called as invert of the tunnel. Here, any point in this semi-infinite space is defined by these polar coordinate system, which is the r theta, where this theta has been taken in an anti-clockwise direction from this horizontal axis, which I am denoting as x axis. The vertical axis is the y axis, and this rock has infinite extent in this direction and in this direction as well. And this h is much larger than the radius of the circular tunnel. As I mentioned, the medium surrounding the tunnel is practically infinite in both the reference directions, which are x and y. Any point in the medium, that is say this point, will be defined by the point called r comma theta. This is simulated in the theory of elasticity as a problem of stress distribution along a circular hole in an infinite plate of thickness T. And this problem of circular hole in an infinite plate of thickness can correspond to the problem of a long horizontal tunnel at depth in the uniform rock formation. The second aspect is the loading. See, this is the tunnel. You have the two reference axes x and y. This is the point defined by r comma theta, where theta is the angle in the anticlockwise direction from this x axis. The radius of the tunnel is a. Now, the applied stress in x direction is Sx, and applied stress in the y direction is Sy. These stresses, they are acting at the boundary of the medium. And where is the boundary of the medium? We saw that we can consider these two extent of the medium as an infinite. So, when this r is tending to infinity, there these applied loads in the x direction and y direction, they are taken as Sx and Sy respectively. So, this Sx and Sy, they are uniformly distributed along the thickness of the plate, which is T. U be the displacement in the radial direction and V is the displacement in tangential direction, which is perpendicular to U direction. The third aspect is related to material properties. So, it has been assumed that material around the tunnel is homogeneous, elastic and isotropic. So, E and nu are going to be the material characteristic of rock around the tunnel. Boundary conditions, as I mentioned, that at a distance away from the boundary, that is at r tending to infinity, this sigma r and tau r theta, they will be due to the stress which are applied at r tending to infinity. And what are those stresses? They are Sx and Sy in x and y direction respectively. Let us see how can we represent these boundary conditions mathematically. So, in this case, your sigma r is going to be half Sx plus Sy plus half Sx minus Sy cos of 2 theta and tau r theta is equal to minus half Sx minus Sy sin of 2 theta, and I write this equation as equation number 1. Now, at the tunnel periphery, which is the stress free boundary and represented by r equal to a, you will have the boundary conditions as sigma r at r equal to a is going to be equal to 0 and tau r theta at r equal to a will also be equal to 0. Make this equation as equation number 2. Now, what exactly is the aim of this study is to obtain the stress distribution around tunnel periphery in the surrounding medium. What do we mean by this? That is, we want to know that what is the pattern of distribution of stresses which are sigma r, sigma theta and tau r theta along both the radial as well as the tangential directions. Plus, we want to know the variation of these stresses along theta equal to 0, means it is going to be the x direction, and theta equal to 90 means along the y direction, and also I need to study the pattern of the distribution of these stresses around the tunnel periphery for theta varying between 0 and 90 degree. Variation of displacement also we would like to see at and around the tunnel periphery, and this variation of displacement we would like to see in the radial as well as in the tangential direction. In the radial direction, this displacement is represented by u, and tangential direction it is v. Now, let us try to see how to obtain the solution of this problem using the theory of elasticity. So, basically this involves the solution of, first is the differential equation of equilibrium for a 2D situation. Let us see what are these equations. So, we have del x of sigma x plus del y of tau yx plus rho x is equal to 0. Mark it equation number 3 1. And other equation is del x of tau xy plus del y of sigma y plus rho y equal to 0. 3 2. Then we need to have the differential equations of compatibility for a 2D situation as well. So, that is given as del 2 del x 2 plus del 2 del y 2 of sigma x plus sigma y equal to 0. Make it equation number 4. Now, when these set of equations, that is equilibrium equation and the compatibility condition, when these are subjected to the set of appropriate boundary conditions pertaining to the problem, these gives us the solution of the problem using the theory of elasticity. Now, what should be the approach towards the solution? So, in this case, Airy's stress function approach is to be used. Now, this Airy's stress function is represented by phi, and we need to assume that there is the absence of body forces. These are rho x and rho y in the previous equations we have seen, or when these are constant. So, in that case we will have we need to apply this Airy's stress function approach in order to get the solution. So, this Airy's stress function phi is defined as sigma x is equal to del 2 phi del y 2, sigma y is equal to del 2 phi del x 2, and tau xy is equal to minus del 2 phi del x del y. Now, just substitute all these three quantities to equation number 3 1. What we are going to get as left hand side of the equation as del x of sigma y, so which is del 2 phi, when you apply these three quantities in equation number 3 1, we are going to get this LHS or the left hand side of the equation as del x of sigma x, which is equal to del 2 phi del y 2 plus del y of minus del 2 phi del x del y, and this is going to be equal to del 3 phi del x del y 2 minus del 3 phi del x del y 2, and this will become equal to 0, which is equal to the right hand side of equation number 3 1. Similarly, if we substitute this in equation number 3 2, left hand side of the equation will become equal to del x of minus del 2 phi del x del y plus del y of del 2 phi del x 2, and this also will become equal to 0, which is equal to the RHS of this equation 3 2. So, therefore, what we get from here is that the stress function, which is phi, satisfies the equilibrium equations. Because equation 3 and equation 3(1) and equation 3(2), they were corresponding to the equation of equilibrium, and we can see that whatever is this stress function, it satisfies these. Now, what will happen to equation number 4, which is the compatibility equation? Just substitute the expression for phi in equation number 4 and you will get an expression like this, that is del 2 del x 2 plus del 2 del y 2 of del 2 phi del y 2 plus del 2 phi del x 2, which is equal to 0. So, this will give me del 4 phi del x 4 plus 2 del 4 phi del x 2 del y 2 plus del 4 phi del y 4 equal to 0. I mark this equation as equation number 5. So, any stress function phi, any stress function phi satisfying equation number 5, that is this equation, will also satisfy equations 3 and 4. So, that is the thing we need to keep in mind. Now, what can be the choice of this stress function for this problem of finding the stress distribution around a circular tunnel in the elastic rock? So, we need to assume a stress function of the form like this: phi is equal to a log of r plus b r square plus c r square plus d r to the power 4 plus e r to the power minus 2 plus f, close this bracket, into cos of 2 theta, and I will make this equation as equation number 6. Now, you see that this phi is a function of r and theta, where these constants a, b, c, d, e and f, these are arbitrary constants which are to be obtained using boundary conditions which are relevant to the problem. Now to proceed further, in the polar coordinate system, this stress function phi is such that sigma r equal to 1 upon r del phi del r plus 1 upon r square del 2 phi del theta 2. This is equation 7a. Then sigma theta is del 2 phi del r2, which is equation 7b, and tau r theta is equal to 1 upon r square del phi del theta minus 1 upon r del 2 phi del r del theta. 7c. See, these equations are the standard equations in the theory of elasticity and can be obtained from any textbook on the theory of elasticity. Now, let us proceed further. So, what we have is the phi, which is equal to a log of r plus b r square plus c r square plus d r to the power 4 plus e r to the power minus 2 plus f into cos of 2 theta. This is what that we have assumed. Now differentiate this with respect to r, see what we get. So this will be a upon r plus 2b into r plus 2c into r plus 4d r cube minus 2e r to the power minus 3, and this f is independent of r, so that will become equal to 0, and here this is cos 2 theta is only the function of theta and not the r, so this will come as it is here, cos of 2 theta. Now 1 upon r del phi del r, what this will become now? A upon r square plus 2b plus 2c plus 4d r square minus 2e r to the power minus 4 into cos of 2 theta. Make it equation number 8a. Similarly, differentiate this expression for phi twice with respect to theta. So, see, this is what that we are going to get, del 2 phi del theta 2 is equal to minus 4 cos of 2 theta c r square plus d r to the power 4 plus e r to the power minus 2 plus f. This term and this term, they are not the function of theta, so therefore when I differentiate this phi with respect to theta, they will become equal to 0. So here what we will get is 1 upon r square del 2 phi del theta 2. This will be minus 4 cos of 2 theta multiplied by c plus d r square plus e r to the power minus 4 plus f r to the power minus 2, and this will be 8b. Now let us further simplify this. So we add equations 8a and 8b. So this is what is going to give us sigma r will be equal to a upon r square plus 2b plus we have the cos 2 theta term in both the equations. So, I just take that common and then I will have 2c plus 4d r square minus 2e r to the power minus 4 minus 4c minus 4d r square minus 4e r to the power minus 4 minus 4f r to the power minus 2. Now, this term and this term will get cancelled, and what you will get as sigma r is equal to a upon r square plus 2b plus minus 2c minus 6e r to the power minus 4 minus 4f r to the power minus 2 cos of 2 theta 9a. Similarly, you will have sigma theta, which was del 2 phi del r 2, that is going to be minus a upon r square plus 2b and plus 2c plus 12d r square plus 6e r to the power minus 4 cos of 2 theta, that is 9b. And from the equation 7c, this will give me tau r theta will be equal to 1 upon r square. You have that expression in terms of the phi and its differentiation with respect to theta and r. So, just substitute it in equation number 7c, and this is what that you are going to get, that is 2 sine of 2 theta c r square plus d r to the power 4 plus e r to the power minus 2 plus f, that is the first term, minus 1 upon r del r of minus 2 sine of 2 theta, and you will have inside the bracket c r square plus d r to the power 4 plus e r to the power minus 2 plus f. So, this tau r theta will be equal to minus 2 sine of 2 theta, and I just take this 1 upon r square inside the bracket and see, this is what that I am going to get, that is c plus d r square plus e r to the power minus 4 plus f r to the power minus 2, and this minus and minus will become plus, and this will be 2 sine 2 theta divided by r, and what I am going to get here is 2 cr, because here I need to differentiate this quantity with respect to r. So, this is what that I am going to get is 2 cr plus 4 dr cube minus 2e r to the power minus 3. So, this will be further simplified, that is tau r theta, you take sine 2 theta common, and what you will get is minus 2c minus 2d r square minus 2e r to the power minus 4 minus 2f r to the power minus 2, and here you will have plus, this is 4c plus 8d r square minus 4e r to the power minus 4. And therefore, what you will get, tau r theta will be equal to 2c plus 6d r square minus 6e r to the power minus 4 minus 2f r to the power minus 2 multiplied by sine of 2 theta. Make this equation as equation number 9c. So, this is how we can get the expression for sigma r, sigma theta and tau r theta in terms of the constants of the assumed stress function phi. Now, we need to substitute the boundary conditions. So, we have the boundary conditions, one was at r tends to infinity and another one was at r tends to 1. So, first let us apply that at r tending to infinity. The boundary conditions are going to be, that is sigma r at r tending to infinity is equal to half Sx plus Sy plus half Sx minus Sy cos of 2 theta. So, what I will do is, I just substitute the expression for sigma r in terms of the constants for phi. So, what I will get from there is this quantity, which is half Sx plus Sy plus half Sx minus Sy into cos of 2 theta. This is going to be equal to the expression which we have got for sigma r earlier. So, that is going to be a upon r square plus 2b plus, I had minus 2c minus 6e r to the power minus 4 minus 4f r to the power minus 2 into cos of 2 theta, this whole thing. And here the condition is that r should tend to infinity. Now, what I will do is, I will compare the terms on this side and this side of the equation. So, comparing the terms on both sides of this equation. So, what we will get is, see here, this is independent of theta and these two terms are independent of theta. So, what we are going to get is half Sx plus Sy, this would be equal to this term a by r square plus 2b. Now, here this r is tending to infinity. So, what will happen to this term a upon r square? This will become equal to 0. So, therefore, this quantity will become simply equal to 2b, 10a. And other term, which is half Sx minus Sy, this will be equal to, see, this is r to the power minus 4 and this is r to the power of minus 2. So, when r tends to infinity, these two terms will become equal to 0. So, this is going to be equal to minus 2c. So, this is 10b. Now, what will happen to tau r theta at r tending to infinity? This is given by minus half Sx minus Sy into sine of 2 theta, or we can write as minus half Sx minus Sy sine of 2 theta. This is equal to 2c plus 6d r square minus 6e r to the power minus 4 minus 2f r to the power minus 2 into sine of 2 theta. Now again in this equation, if we just compare these terms, and obviously this is subjected to the condition that is applicable when r tending to infinity. So when this r is tending to infinity, this term will become equal to 0 and this term will also become equal to 0. But what about this term? See, here you have positive power of r, and when r tends to infinity, this term will also tends to infinity, which is physically not possible. So that gives me the condition that this constant d has to be equal to 0. If this equation needs to have the physical interpretation, then the constant d should be equal to 0. So what we are going to get, if we just compare the terms once again for this equation, so comparing the terms on the both sides of the equation, what we will get is half Sx minus Sy would be 2c plus 6d r square, and of course the condition is there that r is tending to infinity. Now what will happen as a consequence of this, as I explained to you, that as a consequence this d has to be equal to 0. Why? Because no stress can be infinite, otherwise it will lose the practical relevance. So this is practically not possible to withstand it. So therefore what we are going to get is half Sx minus Sy will be equal to 2c. This is our equation number 10c. So this way we saw that how using the theory of elasticity we can approach towards the problem related to the determination of elastic stress distribution around a circular tunnel. So here we have applied the boundary condition at r tending to infinity. We still have few more boundary condition and we still need to find out the complete solution of the problem. So we will continue with this in the next class. Thank you.